Good evening, everyone. நம்ம
Good
லாஸ்ட்
evening, ma'am.
கிளாஸ்ல என்ன டிஸ்கஸ் பண்ணோம்னு ஞாபகம் இருக்குங்களா?
Madam Adila,
What are we
I think
discussing
is
actually?
from Kerala. I think.
Okay, sir. Okay, sir. So, what are we discussing actually? Last class we have discussed a few questions from basic concepts of chemistry, right? And in previous session we have been discussing the chapter called atomic structure, right? Kana, we have started with the chapter, right? So we have been discussing Bohr's model and their formulas related to that. So to calculate energy of an electron, to calculate the radius of the atom and all that, right? So today this session is going to be very important because in this session we're going to discuss what is quantum number and how to write the electronic configuration of an element, which is very important, Kana. And we're going to discuss half-pass principle, Pauli's exclusion principle, Hund's rule. Okay. And after which we'll be moving on to hydrogen spectrum. Right? Shall we start the session? Shall we start the session? How you guys good are in quantum numbers? Are you guys comfortable with that?
Yes, ma'am.
Which class you are from, Adila? 11th or 12th?
11th.
11th standard. Okay, fine. So, shall we start with quantum numbers? So, last class we have done with Bohr's model. We have discussed how to calculate energy of an electron, radius of the atom, angular momentum, and velocity of an electron. Right? Now we're going to start with quantum numbers. There are 4 types of quantum numbers, right? What are they?
Principal, azimuthal, magnetic, spin.
Okay. What is the basic application of quantum number? What is the physical significance of this quantum numbers? Where we are actually applying it? Fine. So, before that, we have to
the electron.
Identifying the position of the electron. Okay. Basically, in an atom, we have protons, neutrons, and electrons, right? We know that protons and neutrons are present inside the nucleus and electrons are distributed outside the nucleus, right? But electrons are arranged in a particular order and which is called electronic configuration. So for every atom we have to know how to write the electronic configuration. Electronic configuration is nothing but basically the arrangement of electron in an atom. So to understand the electronic configuration we have to know what is quantum number and different types of quantum numbers. Okay, fine. According to Bohr, where these electrons are present? According to Bohr's model, where these electrons are present?
Energy level.
Yes, very good. In energy levels. Is there any other term for energy level?
Orbit.
Orbit. Okay.
Orbital.
Not exactly. Orbit is different from orbital, Kana. Okay, let us understand. So now we'll start with quantum numbers. Here is my nucleus, in which we have protons and neutrons, and around this nucleus electrons are revolving in a particular path called energy level, or energy level is also called as orbit, or it is also called as shell. In an atom, how many energy levels are there? in an atom, how many energy levels are there?
Four energy levels.
Sorry, Lakshan?
Four energy levels.
It is not four. That was a good try, but it is not four. Senda Michelvan, any idea? In an atom, there are infinite number of energy levels. It can be hydrogen or it can be helium, it can be carbon, it can be silver, it can be platinum. Any atom, there are infinite number of energy levels. But whenever we are drawing energy levels, we'll be drawing only 4 or 5. That's it, because that is how we can represent, right? Because we cannot draw infinite number of energy level in a board, right? So, but in an atom, we have infinite number of energy levels. So this is first energy level. This is second one. This is third. This is fourth. This is fifth. This is sixth, and so on. So the energy level which is closer to the nucleus is considered to be the first shell. This is second shell. This is third shell. This is fourth shell. This is fifth shell. And this is sixth shell. So this goes on. Okay. Here I am giving the number to the shell, right? And this number is called principal quantum number. The number what I'm giving for shell is called principal quantum number. Okay. How to represent this principal quantum number? Is there any alphabet to represent this principal quantum number?
N.
Very good. It is small n. Okay. So the number what we are giving to the shell is principal quantum number, and the representation is small n. For principal quantum number, minimum value is 1. Quantum numbers are in alphabets also. What are all the alphabets we'll be using to represent this principal quantum number? We'll be using K,
K.
L,
L.
M, N, O, P, and goes on. Okay, but generally we are using numbers, but also we have to know these numbers can also be represented with alphabets. Okay, so this is the principal quantum number. What Bohr told us is electrons are present in shells, but actually in every shell there are subshells. See, this is my shell. Inside every shell there are subshells also. What is subshell? The shell or the energy level which is present inside the shell is called subshell. Okay, so in each shell there are subshells. Inside every subshells there are subshells. The shell which are present inside the subshells are called subshells instead of subshell. See, this is orbit. Orbit is nothing but your shell, and orbital is nothing but subshell. The energy level which is present inside these subshells are called orbital. So orbit is different from orbital. Okay. So the number what we are giving to shell is called principal quantum number. In first shell we have two subshells. In third shell we have two subshells. In second shell we have two subshells. In third shell we have three subshells. Could you please tell me how many subshells are present in fourth shell? How many subshells are present in fourth shell? That's it. So write down the
Seven.
formula. Number of subshells in a given shell number of subshells in a given shell is equal to n. Okay, if the given cell is second shell, then number of subshell is 2. If given shell is 7, then number of subshell is 7. As simple as that. Okay. Now I'm going to give numbers to these subshells, and those numbers are called azimuthal quantum number. The number what I'm giving to subshells are called azimuthal quantum number. See, in first shell, I have only one subshell, right? And the number what I'm going to give to this subshell is 0. In second shell, I have two subshells, and the numbers what I'm going to give is 0 and 1. And in third shell, we have three subshells, and the numbers are 0, 1, 2. In fourth shell, I have four subshells, the numbers are 0, 1, 2, and 3. See, azimuthal quantum number is represented by
Zero.
where is number for azimuthal quantum number?
4, ma'am.
Aha.
Is it
See, for this second shell. In second, two subshells, which is 0 and 1. So the last number is 2 minus 1, right? So the n minus 1, principal quantum number minus 1 is the last azimuthal. So this is azimuthal quantum number. As principal quantum number, we can represent these using to represent these subshells. S, P, D, F. After F, what alphabet will be using? It. So this is the, now we know there are subshells in each shell, and under each subshell we have subshells, and there is a formula to calculate number of orbitals in a given subshell, and the formula is, write down the formula, number of orbitals in a given subshell, number of orbitals in a given subshell, which is 2l plus 1, 2l plus 1. Okay, now the subshell what I'm going to talk about is L is equal to 0, which is S subshell, right? Could you please tell me how many orbitals are present in L is equal to 0 subshell? Number of orbitals in S subshell. What is the formula? 2L plus 1. 2 into 0 plus 1. So only one orbital is present in S subshell, and to represent that one orbital, I have to draw one box. That's it. Could you please tell me how many orbitals are present in L is equal to 1 subshell, that is P subshell? Number of orbitals present in subshell. Yes, it is 3. Because 2 into 1 plus 1, which is equal to 3. And those 3 orbitals are represented by using 3 boxes, and all the 3 boxes are connected to each other. Okay. And how about for L is equal to 2, that is D subshell? How many orbitals are present in D subshell? Come again.
5.
5. Very good, it is 5. That's it. 1, 2, 3, 4, and 5. Okay. So the number what I've given for shell is principal quantum number. The number I've given for subshell is azimuthal quantum number. Now I'm going to give numbers to these orbitals and which is called magnetic quantum number, which is M. Okay. Now I'm going to give numbers to these orbitals and they are called magnetic quantum number. Magnetic quantum numbers are represented using the alphabet small m or small m with the subscript small l. Okay. Now we have to give numbers, right? So it is very easy. See, this is L is equal to 0 subshell, right? In 0 subshell, we have only one orbital whose number is also 0. Okay. Here I have L is equal to 1 subshell and I have 3 orbitals, right? So the numbers are -1, 0, +1. In L is equal to 2 subshell, we have 5 orbitals. So the numbers are -2, -1, 0, +1 and +2. Could you see the pattern here? For example, L is equal to 4. Could you please tell me what are all the magnetic quantum numbers for these subshell? If L is equal to 4, then what are all the magnetic quantum numbers? See, if it is 1, values are -1, 0, +1. If it is 2, values are -2, -1, 0, +1 and +2. If L is equal to 4, then what will be their magnetic quantum numbers?
-4, -3, -2.
-2, -1, 0, 1, 2, 3, 4.
Very good. So -4 to +4 and we have to include 0 also, right? So -3, -4, -3, -2, -1, 0, 1, 2, 3 and 4. So basically magnetic quantum numbers are nothing but -L2 plus L through 0. That's it. As principal quantum number, as azimuthal quantum number, we can represent these magnetic quantum numbers in alphabets. So how to do that? That is also very easy. You have seen. See, for example, L is equal to 0. We have only one orbital, right? So this is my S subshell and this is my orbital and the name of this orbital or representation of this orbital is also small s. Okay. L is equal to 1. This is my P subshell and how many orbitals are there in P subshell?
3.
How many orbitals are there in P subshell? It is 3. And the representations are, see, this is P X, this is P Y, and this is P Z. That's it. Okay. And similarly, L is equal to 2. And this is D subshell. And we have 5 orbitals, right? We have 5 orbitals. I'm going to give you the shortcut to memorize these 5 d orbitals. Listen carefully. See, all the 5 orbitals starting alphabet will be D, but the subscript will be little different. See, let us take X, Y, Z. Okay, here this is D, X, Y and D, Y, Z. Now, last and first alphabet, ZX. Then first 2 alphabets we have to square and we have to subtract them. And this is Z square. That's it. These are all the 5 d orbitals of L is equal to 2. Right? So these are all magnetic quantum numbers. Fine. So we have done with 3 quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number. The number I've given for shell is principal quantum number. The number I've given for subshell is azimuthal quantum number. The number I've given for orbital is magnetic quantum number. And in this orbital only electrons are present. Okay. In one orbital, how many electrons I can accommodate? In one orbital, which means one box,
2.
how many orbitals maximum I can accommodate? Exactly, it is 2. So this is my first electron and this is my second electron. Very good, Kana. Electrons are represented by arrow marks. I can have a double-headed arrow or single-headed arrow. Anything is right. So the number which I'm giving for these electrons are called spin quantum number. And spin quantum numbers are represented by using small s or ms. Okay. The electron which got this upward arrow is called, or the number we are giving to this electron is plus half, and this is minus half. That's it. What this plus what this electron represent and what this electron represents, what this arrow mark represents, Kanna? What these arrow mark represents? Very good. We know these electrons are revolving around the nucleus, right? But these electrons are not just revolving, but they're also spinning in its own axis. Okay. So spinning is nothing but electrons are spinning in its, rotating in its own axis like this. Okay. So if the spinning is in clockwise direction, then that is plus half. If the electron is spinning in anti-clockwise direction, then that is minus half. So this represents clockwise direction and this represents anti-clockwise direction. That's it. Okay. Fine, Kana. So we are done with 4 quantum numbers: principal, azimuthal, magnetic, and spin quantum number. Okay. So maximum number of electron in an orbital is how much? Maximum number of electron in an orbital is
2.
very good. It is 2, right? Okay. In one orbital, I can accommodate maximum of 2 electrons, right? In 2 orbitals, how many electrons I can accommodate? In 2 orbitals, how many electrons I can accommodate?
4.
4, because in one orbital I can accommodate 2 electrons. In 2 orbitals I can accommodate 4 electrons, right? In 3 orbitals I can accommodate maximum of how many electrons in 3 orbitals?
6.
6. That's it. So you're multiplying the number of electrons by, or number of electrons with 2, right? Now my question is, how many electrons I can accommodate in p subshell? How many electrons I can accommodate in p subshell? See, now I'm talking about p subshell. You know, in one orbital I can accommodate 2 electrons. That's it. Now I'm talking about subshell and I'm asking how many electrons I can accommodate in this p subshell. So first job is we have to calculate how many orbital this subshell got, right? How many orbitals there in p subshell? How many orbitals are there in p subshell?
3.
3. So totally how many electrons I can accommodate?
6.
6. So have you got this 3? Is there any formula to calculate a number of orbitals in a given subshell? What is the formula to calculate number of orbitals in a given subshell? The formula is 2L plus 1, right? So if L is equal to 1, then 2 into 1 plus 1, which is equal to 3. So now we are calculating number of orbitals in a given subshell and we are multiplying this number of orbitals with 2 to get number of electrons in a given subshell. So please note down the formula. Maximum number of electrons in a given subshell is 2 into 12 plus 1. So by using this formula, we'll calculate number of orbitals and multiplying it with 2, we'll get maximum number of electrons that particular subshell can accommodate. Okay, so maximum number of electrons in a given subshell is 2 into 12 plus 1. Okay, next question is, how many electron each orbital, how many maximum number of electrons each shell can accommodate. For example, n is equal to 1. N is equal to 1. Kana, in first shell, how many subshells are there? In first shell, how many subshells are there?
One.
Only one. Okay. So what is the number for that one subshell? L is equal to 0, which is S subshell. In S subshell, how many orbitals are there? What is the formula to calculate number of orbital? 12 plus 1. So
Plus
how many
one.
orbitals are there? It is only one. Right. So in this only one orbital, I can accommodate maximum of 2 electrons. That's it. So in first shell, I can accommodate maximum of 2 electrons. That's it, Kana. Now we'll talk about second shell. In second shell, how many subshells are there? In second shell, how many subshells are there?
Subshells.
2, which is L is equal to 0 and L is equal to 1. So this is S subshell and this is P subshell. In S subshell, how many orbitals are there? It is only one. Only one orbital. In S subshell, we have only one orbital, right? And in P subshell, how many orbitals are there?
3, ma'am.
3. That's it.
3.
So, very good, Kanna. So, totally in second shell, how many orbitals are there? 1 plus 3, totally it is 4. So, totally I have 4 orbitals. So, I can accommodate maximum of 8 electrons in second shell. That's it. Now, we'll calculate for third shell manually again. So, in third shell, I have 3 subshells, which is L is equal to 0, L is equal to 1, and L is equal to 2. So this is S, this is P, and this is D. Could you please tell me how many orbitals are there in S subshell? It is 1. Number of orbitals in P subshell is?
1.
3.
P subshell is 3. And number of orbitals in D subshell is?
3.
5. So in third shell, totally how many orbitals are there? 1 plus 3 plus 5. Totally how many orbitals, Kana?
5.
In third shell, how many orbitals totally?
9, ma'am.
9 orbitals. Very good. So in third shell, I have 9 orbitals. So totally I can accommodate 18 electrons. Okay. So now we'll calculate it for n is equal to 4. See, now we need not calculate at all. Actually, number of orbitals in fourth shell is 16. And number of electrons I can accommodate is 32. How I came up with this number 16? It is very easy. See the pattern here. N is equal to 1, number of orbital is 1. N is equal to 2, number of orbital is 4. N is equal to 3, number of orbital is 9. How this 9 came? 3 square is 9, right? 2 square is 14. 2 square is 4 and 1 square is 1. So similarly, 4 square is 16. So number of orbital in a given shell is n square. This is the formula. Okay, please make a note of it. Number of orbitals in a given shell. Given shell is equal to n square. Okay. And next formula is maximum number of electrons in a given shell. Maximum number of electrons in a given shell is 2n square. That's it. We are just multiplying 2 with maximum number of orbitals, right? That's it for now. Any doubt? Any doubt?
No, ma'am.
Okay.
Mm-hmm.
So we are done with quantum numbers. We have done with all 4 types of quantum numbers: principal, azimuthal, magnetic, and spin quantum numbers, and we have discussed the formulas related to that. Now I'll give you a problem. 1 minute. Here is the question. Explain, giving reasons, which of the following set of quantum numbers are not possible. We have to check which set is not possible. Okay. First one, I'll do it, Kana. Listen here. N is equal to 0, L is equal to 0, M is equal to, that is magnetic quantum number is 0, spin quantum number is plus half. We have to justify, or we have to tell whether this set of this set is possible or not. Okay. See, for principal quantum number, we know the minimum value for principal quantum number is 1. But here the value is 0. Is it right or wrong? Is it right or wrong, Kanna? For principal quantum number, what is the value? It should be 1, right? And it is not 0. So, of course, this is wrong because principal quantum number can never be 0. Fine. How about second set? Is it right or wrong?
Right.
Okay. We'll check. L is equal, N is equal to 1. They are talking about first shell. In first shell, there is only one subshell, which is L is equal to 0, and this is right. And in L is equal to 0, I can have only one orbital whose magnetic quantum number is also 0. This is also right. Inside which I can have two electrons, one is plus half, another one is minus half. They are talking about minus half electron, which is also right. Okay. So this is possible set. Okay. How about third one? How about third one? Sorry?
Wrong.
It is wrong. Why? Why it is wrong? Yes. See, this is my first shell, and in first shell I have only one subshell, which is L is equal to 0. But here they're talking about L is equal to 1, which is wrong. Okay. That's it. Okay. How about fourth set, Kana? Is it right or wrong? Sorry? Come again?
It is correct, ma'am.
It is right. Right, Rakshan. So this is second shell. They are talking about second shell in which I can have two subshells. L is equal to 0 and L is equal to 1. They are talking about L is equal to 1 subshell. This is right. In L is equal to 1 subshell, I can have three orbitals. Values are minus 1, 0 and plus 1. And they are talking about M is equal to 0. In which I can have two electrons plus half and minus half. They are talking about minus half electron, which is also right. Okay. This E. Okay. Adila's answer is wrong. Could you please justify your answer, Adila?
Ma'am, his value is 3. In the third shell, the maximum L value is 2.
Yes, right. So Rakshan's answer is also wrong. Yes. Which means that is impossible set. Right, Rakshan? Okay. Because in N is equal to 3, in third shell, I can have only 3 subshells. L is equal to 0, 1 and 2. So L is equal to 3 is wrong. How about F, Kanna?
think it is correct.
It is right. Because in n is equal to 3, I can have 0, 1, and 2. There is about one subshell in which I can have a minus 1, 0, plus 1 magnetic quantum number. They are talking about 0. And in which I can have 2 electrons plus half and minus of this is right. Okay. This question. How many electrons in an atom may have the following quantum numbers? How many electrons can have this following quantum number?
$32, ma'am.
You're partially right, but it is not 30. See, 32 is your what total number of electrons in that shell, right? I think Mumtaz is right. See, she's telling me the number of electrons which can have this quantum number is just 16 and not 32. Answer is 16 and not 32. Could you please tell me what mistake you have done, Adila? Analyze your answer. Bhumika, what is your answer, Sami? What you got?
16, ma'am.
16. Why cannot it is 16? Why not it is 32? Sensible children? You're so quiet today.
Ma'am, is it
Hmm.
the spin numbers is minus half?
Ah, yes. Okay. I'll explain you. And you found what mistake you have done. Sensible children, why are you so quiet today? Is this topic boring?
No, ma'am.
Usually you'll be very active in the class, right? Today you're very quiet. Okay, listen here. In n is equal to 4, that is fourth shell, I can have 4 subshells. L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3. In this L is equal to 3, I can have only one orbital. Here I can have 3 orbitals. Here I can have 5 orbitals. And here how many orbitals I'll be having? In L is equal to 3 subshell, how many orbitals I'll be having?
7.
7. Very good. So in each orbital, I can have 2 electrons. One is plus half, another one is minus half. Right? So they are talking about only minus half electron. So there are totally 16 orbitals. In 16 orbitals, I can have 32 electrons. In 32 electrons, 16 electrons got plus half spin, and the remaining 16 electrons got minus half spin. So the answer is 16 because only 16 electrons can have this minus half spinning. Okay, right. And how about this, Kanna? N is equal to 3 and L is equal to 0.
6, ma'am.
6. Okay, because in n is equal to 3, I can have 0, 1, 2 subshells. Okay, and in n is equal to 0, how many orbitals I can have? Only 1. In only 1 orbital, I can have only how many electrons? How many electrons I can have in only 1 orbital?
2, ma'am.
2.
It is 2. So maximum number of electron is 2. Okay, only 2 electrons can have. Okay, only in L is equal to 0, I can have 2 electrons. Okay, fine. In L is equal to 1, this is not possible, right, Kana? This is not possible. This is also not possible. So maximum number of electron is just 2 and not 6. Okay. You got my point? They are talking about L is equal to 0 subshell. Okay. Shall we move on to next question?
Yes, ma'am.
Ma'am, could you show me the before slide, ma'am? Thanks, ma'am.
Okay, Kana. Next question. An atomic orbital has n is equal to 3. What are the possible values of L and ML? Possible values for azimuthal quantum number and magnetic quantum number. For n is equal to 3, what are all the possible azimuthal quantum numbers?
0, 1, 2.
0, 1 and 2. In L is equal to 0 subshell, I can have only one orbital. So possible value for magnetic quantum number is 0. Here I have 3 orbitals and possible magnetic quantum number is -1, 0, +1. And in L is equal to 2, I have 5 orbitals and values are -2, -1, 0, +1 and +2. Okay, so these are all the possible azimuthal quantum numbers and these are all the possible magnetic quantum numbers. Okay, fine. Second question. List the quantum numbers, that is magnetic and azimuthal quantum number of electrons for 3D orbital. In 3D orbital, could you please tell me the value of L and ML? See, we are talking about 3D. See, this is a way of representing any orbital. The number this represents is principal quantum number, and this alphabet, as we know, it is azimuthal quantum number. Okay, so the principal quantum number value is 3. And what is the value of azimuthal quantum number? It is B, right? So what is the number, Kana?
0, 1, 2.
No. See, it is specifically they are talking about D subshell. If it is D subshell, what is the azimuthal quantum number?
2.
It is just 2. Okay. In L is equal to 2 subshell, how many orbitals are there? 5 orbitals. And their magnetic quantum numbers are -1, 0, +1, +2. That's it. So they are talking about azimuthal quantum number, which is L is equal to 2, and magnetic quantum numbers -2, -1, 0, +1 and +2. Okay. That's it. Third question. Which of the following orbitals are not possible?
One P and 3F.
Okay. 1p and 3f are not possible according to you, Adila, right? Can you please justify
ma'am.
your answer? In 1p, principal quantum number is 1, right? In present, if principal quantum number is 1, they are talking about first shell. In first shell, I can have only one subshell, which is L is equal to 0, which is S. And here they have represented with P alphabet, which is P subshell, which is not right. Okay. Is this orbital possible? Is 2s is possible? Rakshan, is 2s is possible?
Mm.
Yes, because in second shell I can have two subshells, which is 0 and 1. So 0 is possible. If it is 0, then azimuthal quantum number is yes, it is right. It is possible. How about 2p? How about 2p?
It is possible, ma'am.
Yes, it is. Because in second shell I can have two subshells, which is 0, 1, that is S and P. So this is also possible. 3f. Here, principal quantum number is 3 and the values are 0, 1, 2. These are all the possible subshells, which is S, P, and D, and not F. So this is impossible set. I mean, impossible orbital. That's it. Any doubt? Any doubt, Kanna?
No, ma'am.
So we are done with this quantum numbers. Now we'll move on to electronic configuration. See, whenever you're writing electronic configuration, we have to follow few rules. There are three main important rules to be followed. One is half-pass principle, second one is Hund's rule, and third one is Pauli's exclusion principle. What is half-pass principle? What is half-pass principle? What is half-pass principle?
Ma'am, the electrons are arranged in the order of energy, ma'am.
Yes. Whenever you're filling electrons, you have to fill the lower energy first and we have to move on to higher energy. Okay. So electron has to be filled from lower energy to higher energy. That is half-pass principle. Okay. But how to find whether this is lower energy and another one is higher energy? Is there any rule to calculate which is lower one and which is higher energy level? There is a rule called N plus L rule. If n plus L value is less, then that is considered to be the lower energy. Okay. For example, this is 1s, this is 2s, and this is 2p. Okay. Let us understand which orbital got lower energy. Okay. As I've told you already, this number represents principal quantum number and this number represents azimuthal quantum number. As far as azimuthal quantum numbers are concerned, values are 0, 1, 2, 3, 4, which is S, P, D, F, G, H, right? So this is n is equal to 1 and L is equal to 0. So what is the value of n plus L? N plus L is 1 plus 0 is 1, right? What is the n plus L value for 2s orbital? What is n plus L value for 2s orbital?
2, ma'am.
Yes, because it is 2 plus 0, it is 2. For 2p,
3, ma'am.
very good. So could you please tell me among 1s, 2s and 2p, which got lowest energy?
1s.
Very good, Kana. That's it. Right. I'm going to talk about an atom called calcium. What is the atomic number of calcium? What is the atomic number of calcium? How many electrons this calcium atom got?
20, ma'am.
20. Could you please tell me the electronic configuration? Calcium got 20 electrons and we have to fill this 20 electrons from lower energy to higher energy. Could you please arrange and tell me the electronic configuration of calcium?
1s2, 2s2, 2p6.
Hmm.
3s2, 3p6. 4s2,
That's it, right? So this is 10 electron and this is 10 electron. See, this represents principal quantum number. This represents azimuthal quantum number. And this represents number of electrons. In S subshell, I can accommodate totally 2 electrons. That's it. Here also, I can accommodate only 2 electrons. But in P subshell, I can accommodate maximum of 6 electrons. And after which they are filling third shell. Okay. Now I'll teach you how to write this electronic configuration. If you don't know to write this electronic configuration, I'll teach you, or else we'll skip this part. Senthamil Shelvan told this electronic configuration. I've just returned the electronic configuration as he told me. Okay. If you guys know how to write this electronic configuration, then it is fine. We'll skip this part. If you have any doubt in writing the configuration, please let me know. We'll crack this down. Mumtaz, Rakshan, Bhumika. Shall we discuss how to write this configuration? If you guys are confident in writing this configuration, then we'll skip this part. If you have any problem, please let me know. We'll solve it now itself. We'll solve the confusions now itself. Okay. Shall we discuss then? Adila, tell me, Rakshan.
Yes, ma'am.
What does yes mean, Kanna? You want me to skip or you want me to discuss?
Discuss.
Okay, we'll discuss then. How about Adila?
Okay, ma'am.
Okay, what does okay mean?
We'll discuss.
Okay, we'll discuss. Okay, fine, Kanna. So, as Rakshan and Adila asked, we'll discuss, okay? It is very easy. To write this configuration, I'm going to give you a chart, okay? Please understand the chart. Don't memorize it. This is just a shortcut, okay? And I'm going to give this shortcut chart to write the electronic configuration. And this is very, very, very easy. And you don't memorize this chart. Please try to understand, okay? In this chart, I'll write few rows and rest of the rows, you can write it, okay? See, this chart is based on the energy scale. As we move from bottom to top, energy is getting increased, okay? So bottommost is the first row or first energy. This is second row. This is third row. So from bottom to top, I'm writing the chart. Okay. So this is considered to be the first row or first shell. Okay. In first shell, I can have only one subshell, which is yes. This is just the shortcut. Okay. Listen here. This in first shell, I can have only one subshell, which is yes. See, L is equal to 0, 1, 2, 3, 4. Yes, this represents P, D, F, G and goes on. And in first shell, I can have only one subshell, which is S. In second shell, I can have two subshells, S and P. In third shell, I can have three subshells, S, P and D. In fourth shell, I can have S, P, D, F. Fifth shell, I can have S, P, D, F, G. Right? Okay. In first shell, I can have only one subshell, which is yes. We are done with this row. Now we are moving on to second row. In second row, this is 2s. And in second shell, I can have two subshells. One is S, another one is P. That's it. We are done with this row. Okay. Now we'll move on to third row. Kanna, you have to listen carefully from this row. See, this is my third row. So for S and P, write the same number. Since this is third shell, I'm writing the number 3 for both S and P. Now, always you have to write the same numbers for S and P. Now, subtract 1 from this 3, which is 2. S, P, after P, it is D. In second shell, D subshell is not possible. So we cannot continue this. move on to fourth row. So fourth row, so since this is my fourth row, I'm going to write 4 to S and P. As I've told you, we have to write the same number for S and P. From 4, now we have to reduce one number, it is 3. S, P, after P we have to write D. In third shell, D is possible, which means I can continue this row. From 3, you have to subtract one number, which is 2. S, P, D, F. Is it possible to have F subshell in second shell? It is no. Now we have to move to fifth row. Can you please tell me what I have to write in this fifth row? 5S, 5P. From 5, we have to subtract one number, 4. S, P, after P it is D. In fourth row, D is possible. So we can continue here. From 4, you have to subtract one number, it is 3. S, P, D, F. In third shell, F is impossible to have. So I have to terminate this row. Now I am going to sixth row. Can you please tell me for sixth row, Kanna? Sixth row. 6S,
6P,
6P.
5D,
Very good. 5D.
4F,
Very good, Kanna. 4F.
3G.
Very good. Is it possible to have a G in third shell? In third shell, I can have SPD. That's it. So we have to cross this. Now we will move on to seventh row. So 7S, 7P. Next. 6D, 5F. Next. 4G. Is it possible to have a G subshell in fourth shell? No. That's it. If you write this 7 row itself, we can write electronic configuration for all the elements in periodic table. We can write 118 electronic configurations. Okay. Still, we'll write one more row. Okay. For practice, we'll write one more row. Can anyone tell me what should I write in 8th row? Except Rakshan. He told me 6th row, right? Except Rakshan, any of you guys tell me what are all the things I have to write in 8th row? Yes, Adila. 8S.
8P, 7D, 6F, 5G ആണോ മാം?
5G. In 5th row, I can have G subshell. It is right. Okay. That's it. From 5, we can subtract one number, 4. After G, it has to be H, but in 4, there is no H subshell. So we have to terminate this row. That's it. So we are done with this chart. Now I'm going to write n plus L value for all these orbitals. Okay. See, 1s represent one orbital, 2s represents one orbital. Okay. So here, as I've told you already, the first number represents principal quantum number and second alphabet represents azimuthal quantum number. So from for each orbital, could you please tell me the n plus L values? This is 1 plus 0 is 1. This is 2 plus 0 is 2. This is 2 plus 1, which is 3. Kana, please tell me the n plus L value for all these system. For 3s, it is
3S is 3.
Very good.
3P is 4.
Very good, Kana.
4S is 4. 4P is 5. 3D is 6. 5. Okay.
5.
5S is 5. 5p is 6,
Hmm.
4d is 6,
Hmm.
6s is 6,
Hmm.
6p is
7. 6 plus 1, 7.
5d is 7,
Hmm.
4f is 7,
Hmm.
7s is 8,
7 plus 0 is 7.
7,
Hmm.
7p is 8,
Hmm.
6d is 8,
Hmm.
5f is 8,
Hmm.
8s is 8,
Hmm.
8p is 9,
8 plus 1, 9.
9,
Hmm.
6f
This
is
is
9,
9. This is also 9. Very good, Rakshan. That's it. So we are done with the n plus L values also. Now we can arrange the electrons. See, now we are going to arrange for calcium, which we have done already, right? So for calcium, atomic number is 20. So I have totally 20 electrons. According to half-pass principle, I have to arrange electron from lower energy to higher energy. And I have n plus L value ready-made. So I can accommodate the electrons. So which is the lowest energy? Which is the lowest energy, Kanam?
1s.
Very good. And we know in S subshell I can accommodate 2 electrons. In P subshell totally I can accommodate 6 electrons. In D I can accommodate 10 and in F I can accommodate 14. Okay. So as far as S is concerned, I can accommodate 2 electrons maximum. That's it. There is no place here. Now we have to move on to next energy level, which is 2s, right? In 2s I can accommodate maximum of 2 electrons again, right? After 2s, which orbital to be filled? See, I have n plus L value as 3 for 2p and 3 for 2s. See, if both the orbitals got same L plus L value, please check for the principal quantum number. Principal quantum number here is 2. Principal quantum number here is 3. The orbital which got lower principal quantum number is considered to be the lowest energy. Now tell me among 2p and 3s which got lower energy. Among 2p and 3s, which got lower energy? Anna, among 2p and 3s, same got, both orbitals got same n plus L value. But among both the orbitals, which got
3s,
lower
ma'am.
energy? No, no. If n plus L value is less, then that is considered to be lower one. So among 2p and 3s, which got lower principal quantum number?
2p.
2p. Okay. So after 2 years, we have to fill 2p because though the n plus L values are same, principal quantum number is less for this 2p orbital. In p orbital, I can accommodate maximum of 6 electrons, accommodate 6 electrons. After which, obviously, we have to move on to 3s. In 3s, maximum electron I can fill is 2. After 3s, could you please tell me which orbital to be filled? After 3s.
3p.
Very good. 3p. Maximum of how many electrons? 6 electrons. See, this is 2 plus 2 plus 6. So totally 10. 10 plus 2 is 12. So 12 plus 6 is 18. I have 2 more electrons to be filled. After 3p, where I have to go?
4s.
That's it. We are done with the electronic configuration of calcium. This is how we have to write the electronic configuration. Okay. Now, generally we can write the configuration, or generally we'll arrange these orbitals, okay, based on lower energy to higher energy. So initially it is 1s. After 1s we have to fill 2s, after which we have to fill 2p. After 2p we have to fill 3s. After 3s, could you please tell me, Kana, after 3s?
2p,
3p. After that?
4s,
Very good. After 4s?
4p,
3d.
It is 3D because 4p, 3D and 5s got n plus L value as 5. Among these three orbitals, the lower principal quantum number is 3. So we have to fill 3D. After 3D, after
4p.
3D, very good, it is 4p. After which it is
5 years.
5 years. After 5 is
4D.
very
4D.
good, Kanna. 4D,
5p.
very good.
6s.
Next,
4f.
brilliant. That's it. Goes on. So we can fill electrons based on this n plus L values. Okay. Is it clear now? Is it clear now? So this is half pass principle. Okay. This is how we have to arrange electron from lower energy to higher energy. Okay. Now we'll talk about another atom, which is nitrogen. What is the atomic number of nitrogen?
7.
7, ma'am.
Very good. So there are 7 electrons. Could you please tell me the electronic configuration of nitrogen? I want it in terms of S and P. Don't tell me 2, and all that. What is the electronic configuration?
1s2,
Hmm.
2s2, 2p3.
2p3. That's it. Any doubt? Bhumika, Mumtaz, any doubt, Kana?
No, ma'am.
Okay, right. Now this is the electronic configuration. Now I'm going to draw the orbital diagram. See, in 1s, I have only one orbital, and in one orbital, I have 2 electrons. One is clockwise, another one is anti-clockwise spinning. In 2s, I have only one orbital and I have 2 electrons. One is clockwise, another one is anti-clockwise spinning. In 3p, how many orbitals I have? In 3p, p subshell, how many orbitals I have? 3 orbitals. Very good, 3 orbitals. And I have totally 3 electrons. Now we have to know how to fill these orbitals. See, there is no confusion in filling the electrons between 1s and 2s. We know obviously 1s got lower energy, so we have to fill electrons in 1s. After then we have to fill in 2s, right? Among 2s and 2p also there is no confusion because 2s got lower energy relatively, so we have to fill electrons in 2s. After then we have to fill 2p. As far as 2p is concerned, we have 3 orbitals, and please you have to understand that these 3 orbitals are of same energy. See, 1s and 2s, 1s got lower energy. Among 2s and 2p, 2s got lower energy. But in 2p, we have these 3 orbitals. No, these 3 orbitals have equal energy. If orbitals are written like this, then they are considered to be of same energy. If orbitals are of same energy, then they are considered to be, they are called as degenerate orbitals. Okay. So degenerate orbitals are the orbitals of same energy. Whenever you are filling these degenerate orbitals, you should not pair up the electrons. See, which means first you have to fill all the orbitals. For example, I have 3 electrons here, right? First, I can accommodate only 1 electron here. Second electron has to be here. And third electron has to be here. Okay, we should not fill electrons like this. This is wrong. Okay, we have to fill the electrons like this, and this is Hund's rule. Okay, fine. Any doubt? Could you please justify why we have to fill electrons like this? There is a beautiful explanation for this. Why electrons shouldn't be paired first? Any guesses? Definitely you would have studied. It can be state board or your central board. Definitely you would have studied. The reason why we have to fill this, fill these degenerate orbital like this. Okay. Now shall we see the justification? Okay. See, I'm going to do it for D5 subshell. I mean D orbital. Okay, D orbitals. I have totally of 5 D orbitals in D subshell, right? Okay. This 5 represents number of electrons. Okay. So the configuration is D5. So in D subshell, I have 5 orbitals totally. And how many electrons this orbital got? 5 electrons. Okay. Randomly, I've taken 5 electrons. Okay. See, in nitrogen, we have 3 electrons in P subshell. No, similarly, there are 5 electrons in. Okay, let us talk about any atom itself. So you'll not get confused. What atom is this? Could you please tell me what atom is this?